So let's continue. So actually, this is energy storage in an capacitor or in an electric field. So you do some simple integration, you get this 1 over 2 CV squared. So this is actually, I think I have learned this in high school. Yeah. Well, so for small energy, it is VDQ, so very trivial. So we substitute V equals Q over C, and we integrate with respect to Q prime, so it is Q squared over 2C. And we substitute Q equals CV, so one of the C eliminates, so it is 1/2 times CV squared. So the potential energy of a charged capacitor may be viewed as being stored in the electric field between its plates. So it is a physics point of view, so I'm not familiar with this point of view. For engineering students, okay, we just finished the previous half. Okay, we calculate the capacitance and we do all the stuff in the circuit point of view. Although for some situation, the circuit, what you learn in circuit analysis should not be applied. For example, if the circuit is very large or the frequency of the signal is very high, then we need to calculate. We need to consider the EM characteristic. For example, when we design a on-chip inductor, something like that, we need to simulate the EM field, or especially we frequently talk about 5G. 5G use the frequency as high as 28 gigahertz, 28 gigahertz, which is known as the millimeter wave, which means that the wavelength of the EM wave is several millimeter. So the dimension of the circuit is similar to the wavelength, so we need to calculate the EM characteristic rather than regarding the circuit component as the lump circuit element. And for this one, we just it is the energy density. So it is something like U divided by AD. And you substitute C equals epsilon 0 A over D, and also D equals to ED, and then you cancel all the common factor, and then it will something like this. But so for this one, okay. So for this one, an isolated conducting sphere with radius r charge this. How much potential energy is stored in the E field of this charged conductor? So for part A, so it is a sphere conductor. So the C will be 4 pi epsilon 0 R. And actually, we want to calculate the energy stored in it. So the energy is Q squared over 2C. Maybe just now you just saw 1/2 times CV squared, and you substitute V equals Q over C, and then you cancel one of the C, it will become Q squared over 2C. Because in this question, it just gives you Q and R. So you know C and Q. Of course, you can calculate V, and then you still use 1/2 CV squared. So it is. So we substitute C equals 4 pi epsilon R inside, so it will be 8 pi epsilon 0 R Q squared. So it will be 8.99 times 10 to 9 times Q is 1.25 times 10 to minus 9 over 2 times R is 0.0685. So it is 1.05 times 10 to 7 joule. So this is the energy stored in the capacitor. And for B, it asks you what is the energy density at the surface of the sphere. So for B, small u is the capital U over 4 pi R squared. So we plug in all the values. Pi times oh, this is not correct. This is not correct. This is not correct. Do you know why? Anyone know why? So, Okay, actually, um, well, well, actually, for this one, it should be something like, it should be something like the big U divided by the the volume for the energy. But for here, this is the surface area, which is not correct. Actually, it should be something like this. As we know, the E field should be something like this. If it's a sphere, so the charge can be regarded as distribute in the center of the sphere, and U will be like this. So it will something like 32 pi square epsilon 0 r to the fourth. Actually, we have e square and times epsilon 0 over 2. Then, well, so we substitute all the values. 1.25 times 10 to minus 9 square over 32 pi square times 8.85 times 10 to minus 12 times 0.0685 to the fourth. So it will be 25.4 microjoule per meter cube. So joule is the energy. Joule is the unit of the energy, and meter square is the unit for the volume. So actually we use this. So next, well, I think, well, this is capacitor with a dielectric. As I mentioned, for capacitor, we hope if we want to have a large capacitance, so we need to have a large area, or the distance between the two plates will be very close to each other. But actually, we can do some other trick. We put something between the two plates, just like a sandwich. And actually, this is not conductor. This should be something like a dielectric material, which is not conductor. Otherwise, it's not a capacitor anymore. But what is the difference between dielectric and vacuum? Vacuum is 真空 or air. Air would be similar to vacuum for the electrical characteristic. So for this dielectric, it has a dielectric constant called kappa, which is a Greek letter. And this dielectric constant is always greater than 1. Always greater than 1. But for this book, it's called kappa. But if you find the dielectric constant on the other sources, it may be something like epsilon r or something like that. It will be quite a large variation. So actually, you only need to know something like that. For vacuum, it is always epsilon 0. 0 means nothing, so it is same for the vacuum. And actually, when there are some dielectric, it becomes, so you actually only need to change the epsilon 0 to kappa epsilon 0, and that's it. So when we put the dielectric in here, so we'll find that if the potential is unchanged, then you will feel that there are more charge are stored at the capacitor. So it feels like the capacitor will become larger. Or for this case, we try to keep the charge stored at the capacitor unchanged. Then we only need a smaller voltage to make this. So reduce potential difference between the plates are required. So for both cases, it feels like the capacitance become larger when we put the dielectric inside the two plates. So this is some informative stuff. So E field is applied, producing partial alignment of the dipole. Thermal agitation prevents complete alignment. So actually, for the suppose it's free dipole, then actually they will not behave so well. Actually, for example, if it is a break, actually you may be talk with your classmate or maybe going out. So actually, even we apply some uniform E field, the dipole will not align perfectly. It's only partial alignment. molecule with a permanent electric dipole moment show the random orientation in the absence of external E field. So when there are no external E field, it will something like a mass, it will point whatever direction they like. And actually, they will have some repelling or attracting force between them, so it will something like many collision between them, something like the Brownian motion. But for the non-polar dielectric, it's something like during the class. Okay, everyone sit, everyone take a seat, and actually you look at here, or maybe you look at your table. So everyone have similar behavior, and if you apply an E field, they will point to that direction. So for the E field from the left to right, then all the dipole in this dielectric will face to the right, point to the right. And actually, this dipole will generate another E field which has a opposite direction with the external E field, so it will cancel part of it. So the field of the aligned atom is opposite the applied field, which cancel part of it. This is some hardcore physics stuff. So actually, when we put a dielectric inside the plate, the induced charge appears on the plate of dielectric and weaken the electric field between the plates, cancel part of it. So we need to rewrite the Gauss law. Okay, you can see the copper before the E. Yeah, so we'll define the electric displacement we call D, which is equal to kappa E, so that it also absorbs the epsilon zero to make the Gauss law more simpler, like this. So with the dielectric, the Gauss law will have another constant multiply on the left-hand side, but they are more or less the same. So you may regard it as epsilon zero becomes kappa epsilon zero. But the physician likes the D to be defined like this. So nothing special. So for this one, Okay. A pair plate whose capacitance C is charged by a battery to a potential V. The charging battery is now disconnected. So this slab is slipped between the plate. What is the potential energy of the capacitor before the slab is inserted? So this one will be simple. It is something like UI equals 1/2 CV squared, because it gives you everything. So it is nothing but plug in C and V, and it will be 1.055 times 10 to minus 9 joule. So this one is simple. So for the next one, so for this one, what is the potential energy of the capacitor slab device after the slab is inserted? So actually for this one, as we have insert the slab with R equals 6.5, so it will be something like C prime equals 6.5 C. So it is maybe what I don't need to calculate it out. And actually, U prime F is Q squared over 2 C prime. So it will be 13.5 times 10 to minus 12 C times V. V is 12.5 square over 2 times 6.5 times 13.5 times 10 to minus 12. So it will be 1.62
times 10 to minus 10 joule. Okay. Actually, it's something like when you calculate the original capacitor, it will be proportional to epsilon zero. Maybe it's parallel plate, so it will be epsilon zero times A over D. Then now, if we insert the kappa equals to 6.5, then epsilon zero will be kappa epsilon zero. So the C will become 6.5 C, the kappa C, something like that. So the final energy will be 1.62, something like this. And then we need to calculate W equals to UI minus UF. So this is 1.55 times 10 to minus 9 minus 1.62 times 10 to minus 10. So the answer is 8.93 times 10 to minus 10 joule. So we need this weapon if we insert the slab into the capacitor. Very simple, right? So for this one, a parallel plate capacitor of plate area A and plate separation D. So first of all, you just ignore the middle one. The area is A, and the distance between this one and this one is small d. A potential difference V0 is applied between the two plates. The battery is then disconnected. Dielectric slab of thickness B. So we put a dielectric slab of thickness B, and the dielectric constant kappa is placed between the plate. Assume blah blah blah. What is the capacitance C0 before dielectric slab is inserted? So actually, C0 is epsilon 0 A over D. So this is 8.85 times 10 to minus 12 times A. A is 0.0115 over 0.0124. So you should be careful. 115 centimeters squared should be 0.0115 meter squared. So you need to multiply, you should divide 100 square, not 100 only. So it will be 8.21 picofarad. So very simple, just use the simple equation. For the B, what is the free charge applied on the plate? So Q0 would be C0 times V0. And C0 is 8.21 times 10 to minus 12. And V0 is 85.5 volt. So it is 7.02 times 10 to minus 10 coulomb. Still very simple. So what is the electric field E0 in the gap between the plate and the dielectric slab? So for this one, we use the so for Gaussian surface 2, this one. So we can write the Gauss law like this. Actually, there will be electric field going downward. So for the Gauss law, well, not yet. We have not go to the part B yet. So for this one, we consider the Gaussian surface 1 first, because we want to calculate the E field here. So we consider the Gaussian surface here. So for this one, epsilon 0 surface integral E dot dA equals Q. Because only Q is in positive Q is in charge by this Gaussian surface, and actually so it will be something like epsilon 0 EA equals Q0. So E will be Q0 over epsilon 0 A. So it will be 7.02 times 10 to minus 12 as we calculate in part B. And this is 8.85 times 10 to minus 12 times A is 0.0115. So the answer will be 6900 voltage per meter. So this is the E field. The E field at this part. At this part, we will have the E field like that. And for the dielectric, we'll calculate in part D. What's the E field? E1 in the slab. In the dielectric slab. So for this one, it will generate a E1 pointing upwards, cancelling part of the E generated by the outer plate. So for this one, epsilon 0, kappa E1 dot dA for this Gaussian surface. So it will be minus Q 0. So for this one, there are no E field in this conductor and no E field flowing out this way and that way. So the only flux is epsilon 0 kappa E1A. Or actually with a negative sign. Actually, E1 is not generated by that one. Actually, E1 should be something E1 should be something inside the dielectric. Actually, the polarized charge inside the dielectric will still generate a E field, something like E prime, which is opposite to the original E field as we calculate in part C. So E1 will be E minus E prime, something like this. This is E prime. So actually, it makes the E1, which is the E field inside the dielectric, to be smaller than the original E. So actually, the E1 should point downward also. And in this case, the flux is flowing inside, so we have the negative side here. And so it's equals to minus Q0. And now we have E1 equals to Q0 kappa epsilon A, epsilon 0A. So in this case, kappa is 2.61. So it will be something like 2640. So actually, for part C, it is 6900. So it will be 6900 divided by 2.61. It will be 2640 voltage per meter. this case, what is the potential difference V between the plate after the slab has been introduced? So we use V equals E ds. So for the inside part, it is E1. So E1 times B plus E0 is the, well, maybe here I should write E0. Then it will match the E0, something like this. It will match the notation. So for the outside part, the height will be D minus D for this height and this height, and E0 at this part, E0 at this part, and E1 at this part. So the voltage will be something like this. And actually, for this part it is uniform, this part is uniform, this part is uniform. So we plug in all the values, 2640 times 0.0078 plus 6900 0.0124 minus 0.0078. So it will become 52.3 volts.
So originally, if we just, at the very beginning, we don't have the dielectric step, and we use the battery V0 equals to 85.5 volts to charge this capacitor. And after charging, we remove the battery, so it should be 85.5 volts. And then we plug in this dielectric step. Then finally, the voltage will become lower. Some of it is absorbed by this step.
So I think this is the last page. So finally, what is the capacitance with the step between the plate of the capacitor? So it is very simple. C equals Q over V. So it will be 7.02 times 10 to minus 10 over 52.3. Then it will be 13.4 picofarad. Okay. So originally the capacitance is 8.21 picofarad without this left. And after we plug in the dielectric step, it becomes larger, 13.4 picofarad. Almost double. Maybe 1.5 or 1.6 times.